Black holes are known as some of the most extreme objects in the universe. Not even light can escape from them, and space and time are twisted in dramatic ways. We've seen what black holes look like from the outside many times in movies and other media, so that image is probably familiar to us. But what if we were to go inside a black hole? What kinds of scenes would actually unfold before our eyes? For much longer than you might expect, this question stayed purely in the realm of imagination. Recently, however, NASA used precise calculations to create a simulation showing what we might see as we approach a black hole and what it could look like if we were to enter it. In today's video, rather than leaning on cinematic imagination or exaggerated visuals, we'll walk through step by step what we see and how it changes as we get closer to a black hole, staying within the limits of what current science allows. So don't forget to click the subscribe button in the bottom right corner, and let's begin. To create this simulation, NASA's Scientific Visualization Studio relied on Einstein's general theory of relativity. They calculated how matter and energy curve spacetime, and how that curvature in turn affects the paths taken by light. Those calculations were then run on NASA's supercomputer DISCOVER and transformed into the visual simulation you're seeing here. To calculate the spacetime around a black hole, scientists have to solve an enormous number of differential equations all at once, all driven by Einstein's field equations. According to the research team, the process generated about 10 terabytes of data, and the calculations were carried out over 5 days using about 0.3% of NASA's DISCOVER supercomputer resources. The black hole shown in the simulation is set to be nearly the same size as Sagittarius A, the black hole at the center of our galaxy. It has a mass about 4.3 million times that of the Sun and a diameter of roughly 25 million kilometers, making it a typical example of a supermassive black hole. In this simulation, a single virtual camera is placed around the black hole. This camera gradually moves closer and eventually passes into the black hole's interior. Along the way, it shows how spacetime appears to curve as seen by the camera, and how that curvature changes the surrounding view. While this video is the result of calculations, every scene stays within the bounds of observational evidence and theoretical physics. In that sense, this simulation offers one of the closest views we currently have of what would unfold as you approach a black hole. For clearer explanations in today's video, additional materials are also used alongside NASA's simulation results. Whenever you see the NASA emblem in the top left corner of the screen, that scene comes directly from NASA's simulation. Before we dive in, let's give our perspective a name to make the scene easier to follow. From here on out, we'll treat NASA's virtual camera as an astronaut named X. Now let's follow X into the warped space around the black hole. On the right side of the screen, you can see X's position relative to the center, so you can keep track of it as we explore. Ready to follow along? Let's begin. A black hole might seem like something that should be visible even from afar, especially given how it's often portrayed in movies. In reality, however, a black hole emits no light of its own and absorbs any light that falls into it, making it almost invisible from a distance. As X moves closer, however, a bright disk surrounding a dark sphere begins to come into view. This structure is known as the accretion disk. So what creates this bright disk? Gas and dust drawn in by the black hole do not fall straight in right away. Instead, they begin to orbit rapidly around it. As this material spins at speeds close to that of light, friction and compression become extreme, heating it to tens of millions of degrees. The light emitted by this intensely heated material is what forms the accretion disk. But when we look more closely, something starts to feel a bit strange. We call it a disk, yet it doesn't look like the flat, familiar disks we're used to seeing. Although the accretion disk may appear beautiful, what we're really seeing is an extreme demonstration of the black hole's immense power. In ordinary space, it would look like a thin, flat disk, much like the rings of Saturn. But near a black hole, intense gravity warps space itself and bends the paths of light. As a result, light from parts of the disk that should be behind the black hole appears above and below it at the same time. It's as if you're looking at an object straight on, yet somehow seeing its backside all at once. The scale of this accretion disk is hard to imagine. Its outer edge stretches to roughly the distance between the Earth and the Sun, about 150 million kilometers, and even the inner regions extend across tens of millions of kilometers. Now, as the accretion disk begins to fill Mr. X's entire field of view, the scenery around the black hole continues to grow increasingly strange. What we're seeing drifts farther and farther away from the familiar way we normally think about space. At this point, Mr. X is still tens of millions of kilometers away from the boundary of the black hole. Yet even at this distance, the sense of direction we're so familiar with no longer works the way it should. So what does that actually feel like? Let's take a closer look. The scene you're looking at now shows the view directly in front of Mr. X from a point about 16 million kilometers away from the boundary of the black hole. In this region, the black hole's intense gravity strongly curves space, making the universe appear distorted around it, almost as if we're looking through a gigantic magnifying glass. So what are we actually seeing here? First, the dark region you see on the bottom of the screen is known as the black hole's shadow. Even though the boundary of the black hole, the point beyond which nothing can escape, is still tens of millions of kilometers away, the black hole's gravity bends light so strongly that very little of it reaches us from this direction. As a result, we see a completely dark region in the image, not because there is nothing there, but because the light never reaches our eyes. That's why it's called the black hole's shadow. If you think back to how the accretion disk looked when we first observed the black hole, it now appears completely different. We already noticed earlier that the disk looked distorted, but as the warping of space grows even stronger, it becomes difficult to recognize what its original structure was meant to be. The same is true for the Milky Way in the distance. A galactic view that should normally spread out in all directions now seems to collapse inward, gathering into a single frame of view. And at this moment, Mr. X passes beyond the inner edge of the accretion disk and enters yet another zone surrounding the black hole. Even though there are still more than 10 million kilometers left before reaching the black hole's boundary, Mr. X is already being pulled in by its gravity at an enormous speed, about half the speed of light. Here, the behavior of space begins to change in a fundamental way. It's no longer just light that appears to bend, but space itself. From this point on, our familiar sense of up and down, front and back, gradually begins to lose its meaning. The first thing you'll notice in this region is the photon ring. The photon ring is a band-like structure formed when light emitted from the accretion disk is pulled in by the black hole's gravity, travels close to the event horizon, and then, at the last second, barely escapes. But there's something even more surprising hidden here. From a distance, the photon ring looks like a single, extremely thin band, but when you take a closer look, you can see that it is actually made up of multiple layers. This happens because light emitted from the accretion disk follows different paths on its way to the observer. Some of that light, coming from the accretion disk, escapes the black hole's gravity almost directly. Other light takes a far more complex path, circling the black hole several times before it can finally break free from the black hole's immense gravity. As light arriving along these different paths overlaps, the photon ring appears itself as a series of thin, stacked rings. This structure extends far beyond what it might first appear to be. The outermost radius of this region reaches about 25 million kilometers, roughly 65 times the distance between the Earth and the Moon. As he passes through this region, Mr. X is being pulled toward the black hole at about 65% of the speed of light. He is now entering the boundary where even light can no longer escape the black hole's gravity. As Mr. X moves closer and closer to the black hole, he falls toward it at a speed approaching that of light. Before long, he reaches a point known as the event horizon. This is a very special region of a black hole. The moment this boundary is crossed, not even light is able to escape into the outside universe. In other words, anything that happens within this boundary can never send information back to the outside world. The event horizon therefore marks the dividing line between the inside and the outside of a black hole, the point at which a black hole truly begins. Once X finally enters the interior of the black hole, the scene before his eyes actually becomes much simpler than before. This isn't because anything physically disappears. Instead, even though X is already inside the black hole, light and information from the outside universe can no longer reach him, because the structure of spacetime inside the event horizon allows no paths for any signal to make its way in. One particularly interesting point is that the event horizon has no physical substance at all. It is not a solid surface, not a wall, not a barrier in any physical sense. Instead, it is simply a boundary in space-time, defined as the point beyond which information can no longer escape, meaning that information from inside can no longer reach the outside universe because of the black hole's gravity. For that reason, the event horizon itself does not block motion or exert any physical resistance. In theory, an object crossing it would not hit anything or feel a sudden impact at that exact moment. But how large is this boundary, actually? In this simulation, the radius of the event horizon is set to about 12.5 million kilometers, roughly 32 times the distance between the Earth and the Moon. After crossing the event horizon, the most significant change X experiences is not in what he sees, but in how time behaves. From X's point of view, inside the event horizon, time in the outside universe appears to pass faster and faster. This happens because gravity near a black hole becomes so intense that space-time is curved far more strongly than under ordinary gravitational conditions, causing his own clock to run more and more slowly compared to clocks far away. As a result, when he looks outward, the rest of the universe seems to age more rapidly than he does. From the perspective of a distant observer watching this boundary, however, the opposite seems to happen. X's time appears to slow down, eventually looking as if it has frozen in place. This does not mean that time actually stops. Rather, it reflects the fact that strong gravity alters how time flows for different observers. At this point, Mr. X has entered a region from which there is no turning back. Once he crosses the event horizon, every possible future path available to him points inward, leading him deeper and deeper into the black hole. As X moves deeper past the event horizon, his view slowly fills with darkness. For a moment, as everything seems to fade away, he can't help but wonder if this is the end. But that's not what's happening. From this point on, the black hole's gravity begins to affect his body in very real physical ways. As X moves closer to the center of the black hole, gravity keeps getting stronger. But what really matters here isn't just how strong it is, it's how unevenly that gravity pulls on different parts of his body. Unlike on Earth, where gravity pulls almost equally on your head and your feet, things start to change as X falls deeper toward the center of the black hole. The closer he gets, the faster gravity changes from one point to another. At some point, even the short distance between his head and his feet is enough for his feet to be pulled far more strongly than his head. That difference in gravity keeps pulling his body in two directions at once. He's stretched longer and longer from head to toe while the sides of his body are squeezed inward. Bit by bit, he's pulled thinner and thinner until his body starts to resemble long strands of spaghetti. That's why physicists call this spaghettification. By this stage, the forces acting on Mr. X's body have become impossible to withstand. In fact, nothing could survive here. Beyond this point, matter itself is torn apart, broken down all the way to the atomic level. And as Mr. X is pulled completely apart, leaving no trace of the person he once was, his journey into the black hole finally reaches its end. In today's video, we followed the space shaped by a black hole, something that once lived only in our imagination. Together with our astronaut, Mr. X, we traveled from a great distance all the way into its interior. Even in that extreme environment, created by an unimaginably massive object, we caught a glimpse of something remarkable. The laws of the universe were still there, quietly at work. The world of a black hole turned out not to be a place where everything is destroyed in an instant. Instead, it is a realm where the ideas we usually take for granted, space and time, direction and order, slowly begin to lose their meaning, giving way to a completely different kind of reality. And in a strange way, a black hole seems to remind us of something quiet but profound. Even the disappearance of things in the universe is not simply chaos. It follows its own laws and its own meaning. That is all I have prepared for today's video. I will be back in the next one with another fascinating topic. Until then, this has been MC Saloon Studio.